What we discussed last class is this. So we discussed what is a fixed point and when can a fixed point be hyperbolic and non-hyperbolic. Okay. Since we were discussing about 1D maps, so we will have the derivative to decide for our fixed points stability. So how you find a fixed point? If you are given a map xn plus 1 is equal to f of xn, how you find a fixed point? It is the point, fixed point is a point x star such that x star is equal to f of x star. The roots of the equation x star is equal to f of x star gives the fixed point. Yes. And those fixed points, we can analyze the stability of those fixed points because fixed points can be stable or unstable, right? So how can you say fixed point is stable or unstable? So you can say like if a fixed point, so you can see the definition here. A fixed point x star of a map f is said to be hyperbolic fixed point if the absolute value of the derivative of the function at the fixed point is not equal to 1. That means this f prime of x star is not equal to -1 or 1. Then it is known as a hyperbolic fixed point, and we are interested in those hyperbolic fixed points. Okay. So what happens if they don't satisfy this condition? Then they are known as non-hyperbolic fixed points, which are bit special case that we will consider in today's class. So if they are hyperbolic fixed points, so we can start with a theorem, that is, if suppose x star be a hyperbolic fixed point of the map f, okay, then since you are taking the derivative of the function f, what does it mean? Your function f should be differentiable, right? Otherwise, how can you take the derivative? It should be differentiable, right? Otherwise, you cannot take the derivative. So therefore, on the first, we assume this, we make this assumption that f be continuously differentiable, okay? Then if f prime of x star is less than 1, the absolute value, then x star is asymptotically stable, okay? And if f prime of x star is greater than 1, then x star is unstable. Fine. So then I gave you one assignment in class and you guys did that. That is, you take this 1D map, this is a 1D map, and you can see that this is the map and you guys found the stability, right? There were two fixed points and you guys found the stability of those fixed points, isn't it? Agree? Yeah. And I gave this one as homework. I wrote homework also. Okay. And some of you have also taken a photo also, isn't it? Gallery check, gallery check. Anyway, so we will discuss today about non-hyperbolic fixed points. Okay, that another class of fixed points, non-hyperbolic fixed points. So when a fixed point is called as non-hyperbolic, anyone? We already discussed this today. Any ideas? Yeah, equal to 1. Yes. So a fixed point x star, is non-hyperbolic. A fixed point x star is not non-hyperbolic if the absolute value at x star, the absolute value of the derivative at x star is equal to 1. That is f prime at x star is equal to -1 plus 1. Right. So in this case, we cannot have f prime at x star is less than 1 for stability, right? Isn't it? We cannot have f prime at x star is less than 1. Agree? So how can we decide stability of these fixed points? Any ideas? This turns out to be very complex, actually. And I was thinking, shall I give this to you? Can you think I want to make it very natural to you? It should not be that you just saw this theorem and it is just like that. So remember that previously here, let us come to the previous class. When you started with a map F, yes, you took the derivative to check the stability. Now your derivative is not helping you in this case. Your derivative is not helping you in this case for stability. So what can you check? What other factor can help you in decoding the stability of this fixed point? The next derivative. If the function f, you decide that take the derivative and decide the stability, right? Now, if that derivative is not helping you, you should take the next derivative. What is the next derivative? Double dash. Yes. If double dash did not help you, what you should take? Triple dash. So that's exactly going to happen. Okay. So I will write some conditions. It is not going to be very important for your case, but let us read through this. Let us read through this. Okay. Okay. So for that, how to decide stability? How to decide stability? Okay. So if this is the condition, if the second derivative at x star is not equal to 0, okay, if the second derivative at x star is not equal to 0, then you can directly say that x star is unstable. This is the condition. Okay. This is going to be a bit complicated set of theory, but I just want you to see it for one time. Okay. So what you can do, you can just take the double derivative, and if the double derivative at point x star is not 0, it is not 0, then it is unstable. Directly you can say it. Okay. Now, if double derivative is not equal to, equal to 0, then there is a deciding factor. Then there is a deciding factor that if the triple derivative is greater than 0, then it is unstable. Got the idea? Okay. I'll break it down to you soon. And third condition is, so you will ask that every time is it unstable when it is stable. Okay. So it is stable when your triple derivative is equal to 0, fine. Double derivative is equal to 0, but the triple derivative at x star is less than 0. Then x star is stable. Okay. So what are we doing here? Any ideas? What are we doing here? See, first derivative could not help us. First derivative could not help, right? So therefore we came to second derivative. Therefore we came to second derivative, that is f double prime. Now if f double prime, let us do the flow chart. If f double prime at x star is not equal to 0, straightforwardly you can say x star is unstable. No further test. Now suppose the other case happens, that is f double prime at x star is equal to 0, then again the double derivative could not help you because it is equal to 0. The slope is equal to 0, parallel to x-axis kind of thing. So therefore, whom you should take help from? The next derivative, that is triple derivative. So you come back to triple derivative. If triple derivative at x star is less than 0, it is stable. X star is stable. Now if triple derivative at x star is greater than 0, x star is unstable. That's what is written in these 3 points. And this is the flowchart for this. This is the flowchart. Okay. Got the idea? Fine. Shall we see an example? We shall see an example, right? Okay. So take an example. Suppose xn plus 1 is equal to f of xn. This is a 1D discrete map. Agree? Where f of x is equal to minus x cube plus x. Where f of x is minus x cube plus x. Right? Now, can you find the fixed point for this? What are the fixed points? Fixed points. Fixed points of the map. Can anyone tell? How we will solve this? Fixed points. What are the fixed points of the map? So fixed points x star, fixed point x star satisfy. See, how am I writing this? Flow wise, stepwise. Try to write that. Don't skip any steps because it is just simple algebra. Okay, it is tempting to skip steps. Don't skip steps. Most important. X star satisfy. X star is equal to f of x star, right? So x star is equal to f of x star is minus x star cube plus x star. You can cancel out x star from here. So you are left with x star cube equal to 0, implying x star equals to 0 is the only root. Yes. Then x star is equal to the only root, the only fixed point. It's the only fixed point of the map, 1D map. Yes. Then after you compute the fixed point, you should know whether it is stable or unstable. So to know stability, to understand stability, what you do? To understand stability, compute the derivative. Compute f prime at x star. So what is f prime of x? F prime of x is this one. Agree. So what is f prime of x star? It is f prime of 0. That is equal to minus 3 times 0 square plus 1. This is 1. Now this implies that x star equal to 0 is a which type of fixed point? Yes, non-hyperbolic fixed point. So you cannot take the derivative less than 1 for its stability. So who can help you? Double derivative can help you. So what is the double derivative of the map f? Take the derivative of this derivative. Minus 6x plus 0. Agree? Agree? Yes. So what is that implies f prime at x star is equal to 0. If it is equal to 0, you can see that if your double derivative is equal to 0, then you come into the branch where you have to compute the triple derivative, right? So what is the triple derivative? At x star, you have to take the derivative of this minus 6x, that is minus 6. So irrespective of x, that implies f triple prime of 0 is minus 6 and it is less than 0. Yes, it is less than 0. If it is less than 0, what is the case? Yes, it implies x star equal to 0 is a stable fixed point. Your assignment for next class is draw the cobweb. Draw cobweb and check graphically. Draw the cobweb in Python and check graphically that indeed x star equals to 0 is stable, is a stable fixed point. Agree? So this is your assignment next class. Everyone should show me the cobweb of this plot. Okay? Fine? Okay. Fine. Actually, this is the case. This is the case this case holds. This case holds when f prime of x star go to new page. Okay. So this the theorem holds when f prime at x star is equal to 1. That holds only when f prime of x star is equal to 1. So what happens now? The second case. What happens? What happens if f prime at x star is equal to -1? What happens if f prime at x star is equal to -1? So then you have a separate theorem, okay, that is known as a special derivative we need to take, known as something known as Schwarzian derivative. Okay. Schwarzian derivative can help here. Okay. Schwarzian derivative can help here. What is Schwarzian derivative? How many of you have known about it or heard? Anyone has heard of this term? No. Okay. So it is represented as SF, Schwarzian of f at x. It is given by the triple derivative at x divided by single derivative at x minus 3/2 times double derivative by single derivative at x. Then you take the square. Okay. So uh, I think if it comes in the exam, this formula will be given to you. Okay, this formula will be given to you. I don't expect you to remember this formula. So this is Schwarzian derivative. So if f prime of x is equal to -1, then a new type of derivative can help us. That is known as a Schwarzian derivative. You can see it has information. What it takes the information of, it needs the computation of a single derivative, double derivative, triple derivative. So all three derivative, it is inside the Schwarzian derivative. Yes, fine. Now if f prime at x star is equal to -1, then the Schwarzian derivative of f at x star is equal to, okay, minus triple prime x star minus 3/2 of, yeah. Can you see why this happened? Can you understand why this happened? See, f prime at x star is equal to -1, right? So you can replace these quantities, right? With -1. You can replace this quantity with -1. So that's what we did. And then we arrived into this equation. Understood, right? Anyone not understanding this step? Got it, right? So this is the Schwarzian derivative, and the condition is if SF at x star is less than 0, then x star is asymptotically stable. If Schwarzian derivative of x star is greater than 0, x star is unstable. You can relate, I feel, because if the derivative is less than 0, then it is like a decreasing trend. It will approach to some fixed point, right? If the derivative is greater than 0, the value will keep on increasing indefinitely. So therefore, if the fixed point is unstable, the trajectory will grow indefinitely. The orbit will move outwards. Yes. So this is one idea. Let us take an example of this. Let us take an example. So consider the 1D map, that is xn plus 1 is f of xn. And you have this as xn square plus 3xn. Okay. Now the question is compute the fixed points and their stability. Compute the fixed points and their stability. Yes. Can you do that? So x star equals to f of x star gives you x star equals to 0 and x star equals to -2. So one fixed point is 0, another fixed point is -2. Yes. So we have to decide is this stable or which one is stable, which one is not stable. So for fixed point x1 star, what you do? What is the value of f prime of x1 star? Tell me. That is f prime of 0. That is equal to -2. Or sorry, 3. Yes, which is greater than 1. That implies x1 star is unstable. So the case of x1 star is finished, right? Now what is about x2 star? Now for fixed point x2 star, what you obtain? F prime of x2 star. That you are getting as f prime at -2, which you are getting as -1, right? So therefore, who can help? What to do here? Schwarzian derivative can help. SF of x star can help here, right? So what is SF at x star? That is SF at x star is equal to -2. Can you tell? So you have to compute minus triple derivative at -2 minus 3 by 2 times f double prime at -2 squared will come to be -6, which is less than 0, and therefore x2 star equal to -2 is asymptotically stable. So this is the same assignment question 2. Okay, using Python check using cobweb diagrams. Using cobweb diagram, verify stability of both fixed points, x1 star and x2 star. This is the next homework. Okay. So you have to do Python. So the next task is Python based. You have to do 2 Python based codes using cobweb to based on both the maps, 1D maps. The previous map where you were using f prime at x equal to 1, and now this is the case and example where f prime of x is -1. Okay. So practice these problems. These problems are important. Okay. So you can see such type of behavior here. I mean a different behavior in total. Some different behaviors. Some different behaviors before you have considered before is something like this. Concentrate on these figures. Okay. Now this is the function f of x. This is the function f of x and this is the cobweb diagram. Okay. Now what has happened is this is the fixed point. This is the fixed point x star. This is the fixed point. Okay. Now check very carefully that when you started on the right side of this fixed point, this is the initial condition. This is, sorry, this, what is that? So if you, okay. So if you started, maybe we can check it. Yes. So what we were planning is, see this figure very carefully. Uh, See this figure very carefully. Okay. This figure very carefully. Now, this is the fixed point. This is the function f of x. This is the function f of x. Okay. And where is the fixed point? Where is the fixed point of the map? Here. This is the fixed point of the map where it crosses the line y equal to x. Okay. Now we want to analyze the stability of this fixed point. So what we can do? So to analyze the stability of fixed point, if it is a stable fixed point, your iterates will come near to the fixed point. And if it is an unstable fixed point, your iterates will move away from the fixed point. Yes. Now, this is a very different feature which you have not encountered before. Is you take an initial, this is an initial condition. This is an initial condition. This is an initial condition. If you take an initial condition on the right of the fixed point, okay, on the right of the fixed point, you see the cobweb. Where it is going away from the fixed point. It is going away from the fixed point on this side. Agree? Agree. Yes. Now what happens if you take an initial condition on the left hand side? If you take an initial condition on the left hand side, here, then you see it is approaching the fixed point. It is approaching the fixed point here. So on the right side of the fixed point, it is unstable, and on the left of the fixed point, it is stable. So therefore, this kind of behavior is known as semi-stable. On one side, it is stable, whereas on the other side, it is not stable. Okay. So therefore, you can see this is known as semi-stable from the left. This is known as semi-stable from the left. Okay. This is just for your idea. I mean, this is just for your idea's sake. Same thing you can see now. The curvature of the function is different. Now it has bent downwards. Here it has bent upwards. It has bent upwards. Now it has bent downwards. You can see downwards. So when it is bent downwards, you can see this is the fixed point. Okay. Now if you take initial condition, this is one initial condition on the right hand side. On the right hand side, initial right. If you take on the right, then it is coming towards the fixed point. It is coming towards the fixed point. You can see the iterates are coming like this towards the fixed point. But when you take an initial condition on the left, initial left, then you can see, sorry, here it is the fixed point. So initial, it is moving outside, away from the fixed point. So you can see on the right side it is stable, whereas on the left side it is unstable. So it is again semi-stable on the right hand side. Agree? I hope it is clear. Now let us take another case. See this function. Here is the fixed point. Okay, here is the fixed point. If you take an initial condition on the right hand side, then this is moving outside. This is moving outside, this side. And if you take initial condition on this side, it is moving away. So this is totally unstable. Totally unstable. Yes. On both sides, it is moving away from the fixed point. Let us take this case where this is the fixed point at origin. Okay. And you took initial condition on the right hand side. So here the initial condition, you can see it is moving towards the fixed point. It is moving this side. And on the left hand side, it is moving towards the fixed point again, like this. So it is stable. Okay. So these are some of the graphical. So therefore, when I meant that whatever calculations we did today, all the algebraic calculation, whatever you computed, Schwarzian derivative and all, I wanted you to go home and do the same cobweb diagram and analyze via different initial conditions that when a fixed point is stable and when a fixed point is unstable. This is very difficult to do by hand. So use Python to do this. I already showed you one of the Python code where you can plot the cobwebs, where we have seen cobweb of a periodic orbit, cobweb of a chaotic attractor of logistic map. So you can use cobweb for this 1D maps. Okay. Fine. Okay. So this is all about the case of non-hyperbolic fixed points. Okay. Non-hyperbolic fixed points. So, so far, what have we done in this course? So far, what have we done in this course? We understood 1D map. Okay. So far in this course, whatever we learned about 1D maps. What is 1D map? Of the form xn plus 1 is f of xn, right? Then what we understood? We understood that not all maps have fixed points. Okay. We understood that fixed point is one of the simplest invariant set of a 1D map. Okay. What is the definition of a fixed point? It is a point x star which satisfies x star equal to f of x star. So this is a fixed point x star. Okay. Now fixed points can be stable, unstable. Okay. So how can you know when a fixed point is stable? If the iterates approach the fixed point, it is stable. If the iterates move away from the fixed point, it is unstable. If f prime at x star, the absolute value is less than 1, x star is stable. Okay. If absolute value of x star greater than 1, x star is unstable. Agree? Agree? So this is for the case of hyperbolic fixed points. Hyperbolic fixed points. Now for the non-hyperbolic fixed points, what to do? Now what are non-hyperbolic fixed points? When f of f prime at x star is equal to 1, the absolute value. Okay. In this case, how you can assess the stability? It can be two cases. F prime of x star can be 1. F prime at x star can be -1. If f prime of x star is 1, how you do decide the stability? Yeah. Yes, you go to double derivative. If double derivative is equal to 0, straightforward you can say it is unstable. If double derivative is not equal to 0, then you have to take help of the third derivative. So if f prime at x star is less than 0, x star is stable. And if f prime at x star is greater than 0, it is unstable. Right? Agree? This is the case for f prime at x equal to 1. Now if f prime of x equal to -1, how you do it? You compute the Schwarzian derivative of x. Schwarzian derivative of x. If SF of x is less than 0, sorry, x star is less than 0, x star is stable. If SF at x star is greater than 0, it is unstable. So this is the story so far. This is the whole story of two classes done so far. Okay. And we considered an example in each of these following cases. Agree? Okay. Now we move on to the next class of, sorry, this is not equal to 0. Is it? Yes, I think I made mistake here. You mean, yes, this should be equal to 0. Sorry. Thanks. Yes, then there is a separate case. So the branch continues. I did not want to go more. Where? No. So this is what I wanted to tell you, that when f prime is equal to 1, you go to second derivative. And if second derivative doesn't help you, go to third derivative. But when f prime of x equal to -1, then no need to go for second derivative. Directly compute the Schwarzian derivative. That's from many theorems and proofs, actually. Why we did not compute f prime, f double prime here? Yeah, these are special cases. F triple prime can also be equal to 0. Then there will be further cases which we are not discussing. That's a good question. So a lot of cases are still possible, lot of branching can still be done, but those you can go complicated cases. I am just showing you some parts only, not the whole detailed version. So of course, if f triple prime equal to 0, then you have to take f fourth derivative of x star. So like that it will continue. So I mean to say that derivative plays a role in determining stability of the fixed point. Derivative means the slope in 1D maps. Okay. Now let us go to a new aspect, that after fixed points, after learning about fixed points, the next simplest case is the periodic points. Okay. After this, maybe we can take a break. Okay. So next case is periodic point. Okay. So we won't discuss much. So what is a periodic point? What is a periodic point? You take a point x naught, iterate the map f, you go to x1, iterate the map f again, you go to x2, iterate the map f again, you go to x3. But when you iterate this point again, you come back to x naught. So if such a phenomena happens, then it is a periodic orbit. Because you started from this, it went to x1, it went to x2, x3, and again it went to x naught. So again it will keep on repeating. So therefore it is known as period. Okay. So but what is the period of this? What is the period of this periodic orbit? So this is a periodic orbit. This is an example of a periodic orbit. But what's the period? What's the period of this periodic orbit? So what is the period of a periodic orbit? Period of a periodic orbit means after how many iterations the map has come back to the original point, to the original starting point. So can you tell after how many iterations did it come back to the original point? One iteration, second iteration, third iteration, fourth. So it's a period 4 point. So after 4 iterations, it came back to the starting point. It came back to the starting point x naught. Agree? It came back to the starting point x naught. So therefore, can you see something here? Can you observe something here? Okay, what is there is x naught. Okay. What is x1? F of x naught, right? What is x2? F of x1. But what is x1? F of x naught. So f of x naught. That is like f2 of x naught. Agree? Now what is x3? F of x2. How you go to x3? From x2 you go to x3. So what is x2? x2 is f2 of x naught. So f of f2 of x naught, right? So what is this? f3 of x naught. Agree? Similarly, what is x4? There is no x4 actually. There is no x4. So what happens? So x3 is f3 of x naught. Now what is f4 of x naught? f4 of x naught is nothing but f of f3 of x naught. That is f of x3. So what is f of x3? X naught. So what you got here? Can you see something very important here? F of x naught is equal to x naught. F4 of x naught is equal to x naught. And what is this 4 here? The 4 is the period. The 4 is the period, right? So what you got an intuition from this? So suppose if it is a period 5 orbit, suppose a period 5 orbit, x star like this, suppose we have a period 5 orbit, then what is the condition? f5 of x naught is equal to x naught. Agree? Agree? So if it is a period k orbit, what condition you will have? F of k of x naught is equal to x naught. Agree? Agree, right? I mean, I hope you understood. If you have any doubt, please ask. After learning this intuition, we can frame a general definition of a periodic orbit. What is a periodic orbit? Before that, I just wanted to give you a geometrical visualization. What is a periodic orbit? Any doubts? Any doubts here? No doubts. Okay, shall we move on to the general definition? So we are moving to the general definition. You want to see something? Finish. No, not required. Shall I continue? Okay. So we are moving to the definition of a periodic point. Definition of a periodic point. So definition is, suppose x bar is said to be, okay, is said to be a periodic point of f, okay, of f with period k, okay, with period k, if, can you tell me the condition? F composed k of that x bar is equal to x bar. That's what we saw in the previous slide. Yes. For some positive integer k, this happens. For some positive integer k. And it is known as k periodic point. It is known as a k periodic point. Okay. Fine. So how this periodic point looks like? So it is a set O of x, that is like O of x bar, that is like orbit of x bar. Can you tell me the orbit of x bar? It is x bar, then f of x bar, then the second iterate of x bar, so on till, can you tell? No, fk minus 1 of x bar, because why I am not writing fk of x bar? Because it is itself x bar, which is already here. So I am not writing them. Agree? So this is known as the orbit. This is known as the orbit of k periodic point. This is known as the orbit of a k periodic point. So same as a fixed point can be stable or unstable, your periodic point can also be stable or unstable. Okay. So how can you say that if periodic point is stable or unstable? That is the question. Okay, that is the question. Can you think of something? When we wrote this condition, there is something very much rich equation it is. I mean, if fk of x bar is equal to x bar, you are writing this condition, and suppose you say f of k is some function g. You say suppose f of k is some function g, then what you see? Then g of x prime is equal to x prime, isn't it? Does that ring any bell? Does that ring any bell? Yes. Does that ring any bell? What bell it rings? Yes, it is. So it rings that x bar is a fixed point. X bar is a fixed point of G. X star is a fixed point of G. Yes. So X star is a fixed point of G, or what is G? G is nothing but what? Can anyone tell? G is nothing but Fk. G is nothing but Fk. So x bar is a fixed point. X bar is a fixed point of Fk. X bar is a fixed point of Fk. Can you see that? So this is one of the most important results you can see. So finally, what I meant to say in this aspect of study is, finally, when we were studying a periodic point, finally you boiled it down to the concept of a fixed point. So this is the reason why we studied fixed point in the first place, and then we studied to the periodic. You got the idea? So now, if you want to study, if you want to analyze stability of x bar periodic point, it is same as analyzing the stability of the fixed point of Fk, isn't it? What do you think? Is it correct? So I told you, we understood the definition of a periodic point. After that, understanding the definition, what you need to do? You need to understand the definition of a stability of a periodic point. A periodic point can be stable or unstable. So we understood that a periodic point is nothing but a fixed point of the composed map Fk, right? Periodic point is a fixed point of the composed map Fk. So what you have to do? If you want to study the stability of a periodic point, you have to study the stability of Fk, right? So you have to do nothing. What you have to do? Can you tell me? You can tell me. You already have the knowledge. Anyone? So periodic point, let us use this. Periodic point x bar is stable if it is a stable fixed point, if it is a stable fixed point of Fk. X bar periodic point is a stable periodic point if it is a stable fixed point of Fk, right? Second, X bar periodic point is unstable if it is an unstable fixed point of Fk. Now, what do I mean by the first step? If it is a stable fixed point, what do you need to do? Take the derivative. Take the derivative of Fk. Means d by dx of f composed, so on till k times. And that derivative should be less than 1. Right? Are you getting the idea? What I am trying to do here? You told me that f prime at x is less than 1 in absolute value, right? So it is Fk, mind you. What is Fk? F composed with f k times. So can you tell me what is this? Can you tell me what we obtain from this figure? Yes, maybe we can stop here. Okay. So this is the definition of a stability of a periodic point. I meant to tell you that stability of periodic points can be boiled down to stability of fixed points. Okay. So this is the catch. Okay. So after the break, we will start with something very nice. Okay. So we will study some bifurcations and then we will move to fractals. So we will see some pretty pictures. Okay, some pretty pictures and then we'll finish the class. That's the plan of this class. So, okay, we'll meet after the break.